In this video I will look at the local oscillator of the Anglian 3 transverter. I've tried to do something about the sideband noise. The first obvious thing is to replace the amplifier to an PSA 4 5043. It's equivalent, except that it has lower amplitude modulation, noise amplitude modulation, particularly when the coupling capacitor here is small. So I have already replaced it. I should have made a photo of the spectrum before, but unfortunately I happened to destroy it and I don't have any more of them. So this is what it looks like, and these sideband, the shape were completely different with the other amplifier. It had peaks out here, and of course symmetric on the other side. This one has flat regions and something, fairly odd phenomena. What is particular about this oscillator is when I measure the voltage here on pin 4, on the input pin, I have placed an inductor on that point, so I can connect the voltmeter here, and I read minus 0.3 volts. That's a lot of current, so there is rectification inside. Normally this point should be somewhere around plus 0.5 volts. So the amplifier is heavily saturated. And you can see putting this load there improved the noise floor a little bit. Well, I can tune this capacitor here while looking at the spectrum. You can see the noise has a maximum here, and looking at the voltmeter, that's the point of maximum rectification on the input pin. So there is obviously far too much signal. I will solve that by increasing C53. I will put 33 nanofarads here to load this collector by the 50 ohm of the op-amp, and not having a impedance match like it is done now. I have put 0.1 microfarad here to have decoupling on low frequencies. Now that's a decoupling up to the 5 volt line, so to make that quiet I have put a big electrolytic capacitor from here to ground, parallel to C2. This C11 causes a phase shift that approaches 90 degrees, and that means that the tuning of this resonator has to provide a 90-degree phase shift to compensate for that. This is not optimum, so I have removed this capacitor and changed R11 to something much smaller, at this moment 100 ohms, and then and that is to have a low impedance for the crystal to be surrounded by on both directions. The output impedance of the emitter follower should be low anyway, but I want to reduce the power also. So I have made this one much smaller, and I have increased R7, or rather decreased R8, and I have put an inductor across L6, 270 nanohenry, to get the tuning on the right frequency with this. And I have changed this resistor from 1 kilo ohm to 100 ohms and put the trimmer here and also a resistor to ground from here to be able to set the amplitude of the oscillation. What I see on the screen now is I step 10 kilohertz up, and now the signal comes at the center of the notch, and I go back again 10 kilohertz. So now we are 10 kilohertz from the signal. The noise floor here, well, let's clear it. It's minus 116.4, and I click on the signal, and you see the signal shows 0. Well, fairly accurately. So this is minus 146 dBc per hertz. I go up again to the frequency where we do the measurement. That's here. And I switch off the strong signal. And here you can see that the signal, the noise floor, this is the noise floor of the SDRP IP which I'm using. And it's at minus 120. That means minus 150 dBc per hertz. That's the best I can do on 28 megahertz because I don't have notch filters there. Now, going back with the strong signal, you see it is only about 4 dB above. I don't remember what I had. Was it 116.4? That's close to 117. $116.35. Now I can adjust the potentiometer for the voltage on the first transistor of the oscillator. So now I am decreasing the voltage. And here we can see it becomes not so good anymore. And the other direction, I increase it again. And here it's not so good also. So the optimum is somewhere around here. And minus 116.5. That's 3.5 dB from the noise floor. Means that this signal is close to minus 150 also, because the sideband noise plus the minus 150 becomes minus 146.5. So maybe minus 149 dBc per hertz at 10 kilohertz, and I go 10 more kilohertz downwards in frequency. Oops. The level changes because the notch filter, we are a little bit near, so I have to and it looks like there is some kind of a peak on this particular frequency. But the level is reasonably good, and the signal is a little bit above 0 on the scale here. 10 more kilohertz downwards. And again, saturation. Yeah. And here you can see there is not much sideband noise. It's 118, so it means that adding the strong signal rises the noise floor by 0.2 dB, so it is below minus 150 dBc per hertz, and the separation is, I have forgotten, now it's 144.119. 1, 2, 3. So 30 kilohertz. That's the separation where we are below 150. It doesn't look so nice anymore. I will try to clean it up without destroying the last MMIC I have. I have killed some of them already.